Pellet extrusion is a fun and exciting frontier in consumer 3D printing. In 3dprint.id or Metafuse, we built Materium, soon to be launched on the market, that can be attached to your 3D printer. This method of extrusion lets you create really wild mixes of material. This is a vase printed with PLA mixed with coffee. And you may have seen a lot of our other videos that features recycled plastic. And last week, researchers from the Defense University in Jakarta called me if I can make 3D printing work with seashells and silica and PLA. Let's see. They were actually really talking about seashell powders. We call it green clams in Indonesia. They ground it and then filter it in 80 mesh so that they get this fine powder. But they also have another version which is coarser. They didn't filter. I guess they used a different mesh for this one. As you can see, to have this work with 3D printing, we really need the particles to be smaller than the nozzle, but I'm pretty sure this one will clog it instantly. And the silica is basically just another silica. And for the PLA, we're gonna use pure PLA obtained from cornstarch. This is a PLA for sustainable packaging purposes, but they also work in Materium. The machine we're going to be using, we call it Subsolid 1, and it's this one right here. It's got a lot of things we need to make this work. It's got the Materium Pellet Extruder, it's got a built-in hopper, a heated chamber, and what I like about it the most is this emergency stop button. Because when you're working with pellet extrusions, sometimes things go wrong and you want it to stop really fast because the torque that is working on this thing is not child's play. Any material that is to be used will be dumped on top of this hopper. We can't just put these materials and let them like mix randomly. You can't just dunk the material on top because what's gonna happen is finer particle will drop down to the bottom and interfere with the test results. So we need this thing to bond with each other first before dunking it to the hopper. So we created this. This is PLA tachified with ethyl acetate. And then after tachified, they're mixed with the fillers, which are silica and the seashell powders, and let dry. That way, these pellets will carry a maximum amount of fillers consistently from the hopper to the extruder. And to do this, we designed a set of matrix to test the varying amounts of PLA versus silica and the seashell powders. Since I will be handling the machine, I don't want to forget any step. So here we have Indri to help me with that. She designed this test matrix so that every test results will be accurately logged. She will also be helping in mixing and preparing the materials so that I can focus on slicing and 3D printing. They wanted me to print these tiny rectangular cubes. I'm using Simplified 3D and the printer runs on Marlin. Apparently, this shape is used to test radar absorbency. Since this is the Defense University, the research they were doing is actually making stealth drones that is capable of diminishing radar bounce and also disappearing upon crash. That is why they're really interested in making this with PLA and seashells and silica, because in their research they found that those two fillers actually really increases radar absorbency, and PLA would act as a biodegradable material so that whenever the drone crashes, it would disappear one day. We're going to use a rectilinear infill and 100% infill to do this so that we could get pure results from the radar absorbency test. First, I gotta clean out remaining materials previously used by this extruder. You can see that through the small window that this is leftover PLA that I'm going to take away. The unique thing about Materium is that it's basically a very long Bowden extruder. And to do that, we need to extrude around 2 meters of material so that the barrel will be empty. This is what I'm referring to as a barrel. And in pellet extruder, this is a very common terminology. It's got a barrel, a heater, and a screw. This barrel is quite special because it lets you really push the materials in without slipping or rotating with the screw that is spinning during extrusion. We call this thing the mass vectoring barrel. The flashing length is not just this, but it's actually the grooves that spin in the screw, and this equals to around 2 meters of filament. Apparently after the first trial with a 0.6 nozzle, the extruder clogged, so we decided to replace it with a 1.5 millimeter nozzle. These are pretty fat extrusion lines, and this would only take around 20 minutes of print time. This is the control PLA, pure unmixed PLAs serving as the control. Here you can see the difference between a 10% loaded PLA and a 20%. It's a lot more darker, so the print should come out darker too, and we'll hope that as the filler amount increases, the radar absorbency will be better. So this is the control PLA, it's pure PLA. Now we're going to flush it. And this is 20% versus 30%. At 30%, it's now not stringy like PLA, although this is 220 degrees Celsius, and a lot more of bubbling and popping starting to occur. Let's see how this prints. It's kind of foaming. And cleaning this thing up is quite a pain in the beep. We're gonna have to do this for, I don't know, dozens of times. So, gotta keep up. Pure shell powder is done. We're going to flush the barrel and everything in it with polypropylene. This is a very good material to flush with. First thing first is really apparent when it does its job because it's clear or translucent. Second, in my experience, they really polypropylene really do flush everything inside the barrel. So let's go. So we spilled the flushing material. The pipe got detached. Lucky we got this handy vacuum cleaner right here. Like, this is something you need to deal with pellet extrusion like on a daily basis. You can start seeing that clear polypropylene starts to coming out instead of this PLA seashell mix. So this is PLA with silica. This is much better to look at than whatever this is. We now have a quite stable PLA and silica extrusion. The constant popping may come from the fact that silica absorbs a lot of moisture, so this is natural actually. I raised the temperature, lowered the temperature, raised the flow up to 130%, but these pops still happen. I'm not sure why. What should happen is these pops should be gone by raising the multiplier, because I thought this was lack of volumetric flow, but that doesn't seem to be the case. apparently raising the multiplier fixed the popping effect. It's not gone, but now the extrusion is acceptable. So I think this happens because silica absorbs a lot of water, and in that process, it made the mix to physically expand and make it less dense. We need a lot more extrusion or flow to compensate for that. The extrusion seems to inflate and then deflate. Look. So the print is looking a lot better. The extrusion process due to the silica popping is a lot less now, even though I'm using much lower extrusion multiplier. It was 130 before. So it's confirmed that reducing the silica content is having a positive impact on the print, but only in this case where you mix the pellets using my wet loading method. So the print failed because it got off the build plate, but this is interesting. Let me show you something. This is like toothpaste. That's all. So the thing is with this experiment that you have to understand that we can't use the same flow rate for all composites, because apparently silica really foams the extrudates, and although it lays down fine, it makes these. And this raised proportions knock the print off the bed, so I gotta use like 90% multiplier just so that it prints fine. It's working like other specimen, so you have to understand that adjusting flow rates for each print, although I think that kind of makes the print inconsistent, the test inconsistent, so but we still get solid fills. I actually broke some of the print here. You can see the cross section. It's white, it's hard to see, but they're solid, and this is what matters, instead of using the same flow rate for each specimen. Maleic anhydride and methyl ethyl catone. I'm trying to make a grafting solution for polymer pellets so that you don't need a twin screw extruder to mix between any two incompatible polymers in pellet form. This video is confidential. So I just made functionalized PLA by grafting it with maleic anhydride by using the MEK plus MA solvent wetting method in basically a desktop sized lab. We can call this compound PLA GMA or PLA grafted maleic anhydride. It's actually the sort of technique that industries use to create blends. So PLA plus or ABS plus, they are usually mixed with other counterparts like PC, nylon, TPU, but they don't normally blend well together because they come with different surface energy, also polarity mismatch, and that's where MA or maleic anhydride comes in. So what's the proof that I just made PLA GMA? This is what would come out of the extruder. This sort of bubbling mess. It's like, if you ever watch it, if you ever seen it, it's like two slugs mating with each other, because PLA and PP is basically very incompatible. So they would just stream differently. And after I flushed PLA GMA with PP, this was the extrudate, and you can see this is a smooth extrusion. This is a PLA PP blend. So PLA GMA made with Materium Pellet Extruder in And in the desktop, without a twin screw extruder, functionalizing PLA with basic chemistry works.